So this is the second of two chapters that to me seem kind of technical. In chapter 4 we needed to talk about how objects move here on Earth, and actually we can apply that, what we understand about objects moving, motion, the laws of motion on Earth, to celestial objects. And in this chapter we need to dive into kind of the nitty-gritty of what we generally call electromagnetic radiation or light. So one of the things that that astrophysicists I think do quite well is to just get every little bit of detail they can of information coming from celestial objects such as stars and just generally galaxies, black holes. So what you're looking at here actually is a fingerprint. We're going to come back around to this slide in a minute, but does it look like DNA? You know how like you take DNA and they run them on these plates and it separates into these bands and they can identify the location of markers. Actually, this is a fingerprint of our sun, and those black lines are what we call dark spectral lines, and they are an indication of actually what's chemical composition of our sun. So we need to talk about different types of light energies. Now, broadly speaking, light is a member of what we call electromagnetic radiation, affectionately called EM radiation. So light is just one of many energies on what we call this kind of spectrum. You know, there's like, if you say light can be broken out to a spectrum, you're saying like the colors of the rainbow. Well, actually, these electromagnetic radiation energies lie on either side of visible light. So you've probably heard these names before, gamma rays, and actually they're written here from highest energy to lowest energy. So we have gamma rays, X-rays, ultraviolet radiation, and then actually right here between ultraviolet and infrared is visible, and this probably information you want to get on your note card to bring with you to your unit exam. So on the long side of what we say visible, or the less energetic side of visible, we have infrared, microwaves, and then radio waves. So I just think it's amazing that astrophysicists actually can gather this information from distant objects and have it make sense. It's just a piece of the puzzle to understanding our universe. It's just amazing. One of the things, or a few things about these different, sometimes I call them cousins. Okay, if you hear the word cousins from me, okay, cousins and different forms of EM radiation, this is probably what I'm talking about. Okay, these different forms of electromagnetic radiation. What they all have in common, they have some very important things in common, and actually they can morph from one energy into another. Okay, that's so cool. They all travel in a vacuum, actually at what we call the speed of light, and the speed of light is the variable c, and they travel is both what we say, they have that dual nature. So they have a wave sort of component to them or property to them, and then they have a particulate particle property to them. That particulate little packets of energy we call photons. So all of those energies have this going on for them. They have this in common. So if we take a look at just a waves, what do we mean by waves? Well, this actually is if you were to fix a rope onto a wall and kind of move the rope up and down, you would create this sort of wave pattern. This actually is what we call a crest, and right here this is called a trough. Okay, and then from crest to crest or from trough to trough, it's literally a distance, okay, is what we call the wavelength of the wavelength of the wave. Okay, the wavelength of the energy, the wave of the energy. So this is a distance usually in meters, okay? So all those cousins, they have different wavelengths. They also have different frequencies. And a frequency, let's see if I can kind of scroll down here. The way I describe frequencies is basically you have an energy that's moving through space. Okay, here's my energy moving through space. Okay, and here's my wave. Okay, it's moving. I know it looks like it's not, but it is. Basically, if you were to stand here and count the number of waves that pass you in 1 second time, okay, that actually would be the frequency. So frequency are waves per second, waves per second. And so the units of waves per second or per second are the hertz, or hertz. So frequency is in units of hertz, waves per second. And so I just think it's amazing. Here in a minute you're going to see like how many cycles, how many waves of these radiate energies pass a point in 1 second, and it's just amazing. So for all of the cousins, as long as they are moving in a vacuum, I can never spell vacuum, as long as the medium is like absence of particles, of vacuum, they all travel, like I said, at the speed of light, and which is a really high number, 186,000 miles per second. And for any given cousin, if you take its wavelength, by the way, I didn't emphasize it, but I think you saw me, this symbol right here, it's a Greek letter lambda, is actually wavelength, the variable we use for wavelength. For any cousin, its wavelength times its frequency is a constant. It's the speed of light. Okay, it's not magic here. Basically, you're taking the cycles per second times its wavelength, and you get units of meters per second, and that's actually its speed. Okay, so those are the cousins. Now let's take a close at them coming up. I really like this figure from your textbook. Okay, so this figure from your textbook will kind of start at the top and move on down. I think it's from your textbook. You can actually see the names of the cousins. Okay, I'll call gamma rays 1, X-rays 2, ultraviolet 3, visible 4, infrared 5, microwave 6, and radio wave 7. Okay, there they are, kind of from left to right. With regard to wavelength, okay, this is wavelength. Okay, these the shortest, and over here, scoot this over, this is the longest. Okay. With regard to frequency, the frequency is down one more. With regard to frequency, the short wavelength means a high frequency. A long wavelength means a low frequency. So let's look at some of these numbers. So with regard to wavelength, okay, like how long is this repeating unit? So if we pick on something here in gamma rays, okay, this is in units of meters. So basically it's 1 times 10 to the negative 12th meters. Okay, and I think we talked a little bit about scientific notation in here. What that means is I basically need to write, let's see if I can do this, 0. And I need to move the decimal place over 12 places that way. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, there-ish. Okay, and the number 1, meters. Okay, so that's how small that's a fraction of a meter that gamma rays are, with the wavelengths of gamma rays. That is so cool. If we compare to actually up here, the radio waves, okay, so 10 squared, so this is gamma, this was gamma wavelength. How about radio wavelength? Radio wavelength, okay, it is 10 squared, so 10 squared is what? 100 meters. Okay, so take a yardstick basically and put 100 of them, and that is a repeating unit of a radio wave. Okay, that's how long one single radio wave is. So actually that has consequences, because when we talk about different types of astronomy that goes after these different energies, we're going to see that their telescope needs to be different. So then what your author does is on the same table kind of talk about everyday objects. How big, for instance, are X-rays? Okay, well, the wavelength of an X-ray falls into the ballpark of the size of a hydrogen atom. Visible light, okay, about the size of bacterium. Infrared and microwaves, about the size of the pinhead of the head of a pin. Microwaves, radio waves, about the size of a baseball. Radio waves, though, can be very long, okay? So that's how that all works. I like then what your author's done kind of from left to right here. Everyday objects, what would we be concerned with regard to, for instance, X-rays or gamma rays? Okay, radioactive elements, X-ray machines. With regard to visible light, a light bulb. Okay, with regard to infrared. Now, one of the things I should kind of give you a heads up about infrared is actually thermal energy or heat. So it's really cool that, no pun intended, that actually in astronomy we can look at, for instance, stars, baby stars, and see kind of their little heat signature and get a sense for what they're doing. But what your author's done here is say that actually people ooze infrared radiation. People ooze thermal radiation. That's kind of cool. Radar, microwave ovens for these longer wavelengths. Okay. So now the last little line up here basically again kind of goes from left to right, the different energies, and it says, all right, so what about celestial objects would you be interested in? And gamma ray bursts actually are energetic events associated with perhaps the formation or a feeding black hole. Speaking of black holes, in the X-ray region, we can actually get energy. If matter is kind of in queue to go down a black hole, that matter is going very fast, and it gives us these X-rays. With regard to ultraviolet radiation, actually the sun is being studied in all sorts of different energies, but we can get some good information about the sun in ultraviolet and visible. With regard to infrared, we can actually see baby planets and stars forming. With regard to longer wavelength energies, the cosmic microwave background in microwaves. The cosmic microwave background actually is the Big Bang. I'll just put BB for Big Bang here. Okay, and then here, this last one here, very long wavelengths, very long wavelength energies, radio waves. Actually, we can understand distant galaxies, how they are evolving and living by studying the radio waves that they're sending us. So awesome stuff. So this slide kind of looks at three different wavelengths and try to get three different energies, excuse me, at different wavelengths. Try to get a fix on wavelength and frequency a little bit. So if we consider kind of wave A, wave B, and wave C, here with wave A, let's just kind of go with a wavelength of 1 centimeter and a frequency of 30 gigahertz. Okay, so the frequency is 30 gigahertz, the wavelength is 1 centimeter. Giga, by the way, means 1 billion times the base unit. Okay, so 1 billion per second. Oh, goodness. In 1 second, you get 1 billion of these energy cycles that pass a point. That's pretty cool. So that's wave A. What about wave B? And these are cousins. They are different energies of electromagnetic radiation. Here with B, then notice what your author's done is basically take the wavelength and cut it in half. Instead of 1 centimeter, it's a half a centimeter. If you do that, then you're going to have to double the frequency. So instead of 30 gigahertz, the frequency is 60 gigahertz. Okay. For wave C, if we compare wave C and wave A, okay, wave C actually is the wavelength is a lot shorter. It's just a quarter, okay, of a centimeter instead of 1 whole centimeter. So then that will automatically increase the frequency by a factor of 4. So your frequency is 4 times 30 gigahertz or 120 gigahertz. Okay, so all of these cousins, and you'll have to just kind of bear with me. When I translated this into explain everything, my lambdas didn't come over. So this actually, well, maybe this is a times. Okay, this should be wavelength times frequency is equal to speed of light. So at the bottom of this, you probably have it on your slide. So wavelength times frequency is equal to the speed of light. Okay, so that's kind of how that all. So just one kind of quick look at that sliver, that little cousin that we call visible light. So I hope you're getting kind of a sense of how visible light is just inserted into what we call a continuum of energies called electromagnetic radiation. So here we have one of the things that Newton did was you take white light, okay, white light, and you pass it through a prism, and you can actually get that white light to separate into its components. So here in a minute I'm going to kind of show you a mnemonic device, but can you see going from this end over, we have red, orange, yellow, green, okay, blue, indigo, violet. So violet's here, red is here, violet's here, okay. So just kind of focusing on the colors of visible light. That whole red, orange, yellow, green, blue, indigo, violet. One way you can memorize it, if you think of a person's name, okay, the first name of that person is Roy, his middle initial is G, and his last name, I've never run into anybody with this last name, but is B-I-V, as in victory, okay. So if you do that, then you basically have the color, all of the components of white light in from the longest wavelength to the shortest wavelength. Okay, so just to kind of put things in perspective, one of the things I think is quite handy is that if you go ahead and write the colors of the components of white light using the Roy G. Biv, well, however you want to do it, red, orange, yellow, green, blue, indigo, and violet. What we have here, just a little bit longer than red. The color red is infrared. Just a little bit shorter than the color violet, we have ultraviolet. Okay, so that's kind of cool.